Hello guys, this is physics form 2. The first lesson, the first topic in form 2 is magnetism. Magnetism. We are going to talk about magnetism and see how it will be set and see how it will be set in KCC when we will be revising for that. So this is the side of syllabus coverage. If you need revision, we have physics KCC revision videos, you can watch that. But if you are homeschooling, you want to cover syllabus faster, then you can use this channel. This is Victor online learning platform. I am Mr. Victor, a graduate from ZTech University. So we are going to start. This lesson is going to take 1 hour maximum. So we are going to start with magnetism, the other chapter 1. As we introduced physics, I said that magnetism is a branch of physics, and we saw what it deals with. In our first class, we did that. So magnets are substances that are able to attract and hold items. Magnets are substances that are able to attract and hold items. Lodestone is the only known natural magnet which was discovered by the Chinese 2,000 years ago. Magnets and non-magnetic materials. Magnetic materials are those that are strongly attracted by magnets, while non-magnetic materials are those that are not affected by magnets. So magnetic materials are materials that are strongly attracted by magnets, while non-magnetic materials are not affected by magnets. Iron, steel, cobalt, and nickel are magnetic substances, while wood, glass, and copper are non-magnetic substances. Substances that are repelled by magnets are said to be diamagnetic, whereas those which are strongly attracted, like iron, nickel, cobalt, are called ferromagnetic materials. Kindly note that substances that are repelled by magnets are called diamagnetics, and those that are strongly attracted are called ferromagnetic materials. The materials that are strongly attracted, such as that the magnet seems to have no effect on them, are called paramagnetic materials. Ferrites are a mixture of iron oxides and barium oxides, and the most newly developed magnetic materials. Ceramic magnets or Magdora magnets are made from the ferrites and are strong. What are the properties of magnets? They are double-poled substances with both the north and south poles. Like poles repel and like poles attract. Repulsion is a sure method of determining whether two substances are magnets. So in exam you'll be told, what is the surest test for polarity? We have said it is repulsion. Why? It only happens between unlike poles. So it only happens between like poles. Repulsion is the surest test of polarity. Why? It only happens between like poles. Why are we not saying that attraction is the surest test? Because attraction is not the surest test of polarity, because it happens between unlike poles and also between a magnet and a magnetic material. But repulsion only takes place between like poles. The third one, the greatest magnetic force is concentrated around the poles of a magnet. The greatest magnetic force is concentrated around the poles of a magnet. Magnetic Field patterns. Magnetic field patterns. What are magnetic field patterns? Magnetic field is the space around a magnet where a magnetic field or force is observed. A line of force gives the direction of the magnetic field at each point along it. This closeness is a measure of the strength of the magnetic field or of the force that will be exerted by the bar magnet. Examples of magnetic fields. So you can see we have that. So what you're supposed to remember, that magnetic fields, they originate from north to south. So as you can see on the diagram, then you have said they concentrate at the end of the pole, as you can see. Then so from the diagram you can see that. So kindly note, if you are drawing a magnetic field, kindly they should not cross each other. They should not cross each other. As you can see, the diagram we are still talking about. So you said magnetic fields originate from north and goes to south. Kindly see what is happening. Kindly see the diagrams. You have the neutral point marked X, where the magnetic field or effect is not felt. That is a neutral point X. So we have soft ion now placed in between. So magnetic fields will pass through the ion, because ion is a magnetic materials. It will get magnetized. Once it gets magnetized, then the magnetic fields will pass through it, as you can see in the diagram. Then we have this ring here, neutral point X. This is where magnetic field is not, or magnetic effect is not felt. Again, you can see in the diagram that. So kindly mark that. So the point marked X are called neutral points, where there is no magnetic field at such points. So X are neutral points where there is no magnetic field at such points. Watches, non-digital electron beams in the cathode ray tubes and TV sets are shielded from external magnetic fields by placing a soft ion cylinder around the neck of the tube or watch. Making magnets. How do we make magnets? The following are the methods used to make magnets. So we have magnetic induction. What is induction? This is the process by which magnets are made by placing ferromagnetic materials in a magnetic field. Materials like iron lose their magnetism easily and are said to be soft, while others like steel gain magnetism slowly but retain it longer, and they are said to be hard magnetic materials. So and are used to make permanent magnets. So if you are told to differentiate between soft magnetic materials and hard magnetic materials, you simply say soft magnetic materials, these are materials which are easily magnetized and they easily lose their magnetism, while hard magnetic materials are materials which are hard to magnetize, but once they are magnetized, they are very difficult to lose their magnetism property. Kindly note that. Number 2, we have magnetizing by stroking. Magnetizing by stroking, because you can see on the diagram, the object to be magnetized is placed on a bench, then a bar magnet is dragged along the length of the bar from one end to the other. This is repeated several times and the object becomes magnetized. This method is known as single stroke method. The one you are seeing on the diagram is known as single stroke method. As you can see, if you are magnetizing using a stroking, the end at which you make a corner or you turn will acquire the opposite pole to the one in contact of the bar magnet. So it will acquire the opposite pole. So you see here we have North Pole. So the end at which you make a corner will acquire the opposite, which is going to be South Pole now. So as you move in clockwise direction or whatever direction you are going, the point at which you turn will acquire the opposite pole as that of by magnet. So this is a single stroke method. Magnetizing using an electric current. This is the use of magnetic effect of an electric current through a solenoid insulated wire of many turns. So that is what a solenoid is. So a solenoid is just an insulated wire of many turns. So as you can see on the diagram, from here we'll go deeper later in the topic, where we are going to know how will we know the polarity of the magnet. So here we are going to use the rules. There are some rules: right hand rule, screw grip rule. That. So you have current, then you have bar, then you have battery switch, then you have solenoid. Demagnetization. So you also have hammering. So demagnetization. So what is demagnetizing? Demagnetizing is the process of removing a magnetic property of a magnet. The following are the methods that are used to demagnetize a magnet. So hammering them hard with their poles facing east-west direction. Why do we hammer them with their poles facing east-west direction? So number 2 is hitting them strongly. Number 3 is placing a magnet inside a solenoid and passing an AC current through it for a short time. Caring for magnets. How do we care for magnets? Magnets should be stored in pairs with unlike poles adjacent to each other, attracted or attached to pieces of soft iron called keepers. Magnets should not be hammered, especially with their poles facing east-west direction. Magnets should not be heated strongly or dropped roughly on surfaces. Magnets should not be placed near alternating currents. Magnets should be kept dry and clean, since rust can make them lose their magnetism. You have uses of magnets: used in making other magnets, used in making loudspeakers, used in making oil meters. Then the last one, used in making telephone speakers. Domain theory of magnetism. In a ferromagnetic substances or materials, small atomic magnets form large groups called domains. These atomic magnets face one direction, where the direction varies from one domain to another. In unmagnetized crystal, the direction of these domains are different, hence their resultant magnetism is zero. So as you can see in the diagram, so you have unmagnetized and magnetized. Unmagnetized, the domains are facing any direction, and therefore their resultant magnetism is zero. Then we have magnetized material. These domains are facing one direction. The magnetic domains are facing one direction, hence we say they are magnetized. When a magnetic material is placed in a magnetic field, the atomic magnets rotate, and eventually all domains face the same direction. When this happens, the material becomes magnetized. When a material is magnetized, we say it is saturated. This means that the magnetism of the material cannot be increased by any other method, and this is the domain theory of magnetism. Let's move to chapter 2, which is measurement 2. So measurement 2 is a very important topic which is normally being set in your exams, and it will be there in paper 1 or paper mostly paper 1. So we have in measurement 2, we had talked about measurement 1 in form 1. You can check that out. If you missed it, you can check it out. So we have Vernier calipers is used when higher accuracy in measurement is required, and this cannot be done using meter rule. Vernier calipers has two scales, main scale and vernier scale. Outside jaws are used to measure both the length and the external diameters. Inner jaws, inside jaws for measuring internal diameters, while the tail is used for measuring the depths of cavities. The main scale is divided into centimeters and millimeters. The vernier scale is divided into 10 equal divisions of 0.9 millimeters each. The accuracy of vernier calipers is 0.10 millimeters. So this is the vernier calipers we are talking about. You have seen it, you have interacted with it in your laboratory when doing practical. So that is it. So you have vernier scale, main scale, you have jaws, you have ears, then you have tail. The reading is taken in 2 steps. The main scale is read at 0 mark of the vernier scale. The values given in centimeters. The vernier is read at the position where the mark on the vernier scale is exactly lined up with a mark on the main scale. The values are given as 2 decimal places of a centimeter. For example, we have this, give the reading in the following diameter. So as you can see, where there is a coincidence, so we are going to have a value before 0. So main scale value before 0 is, so you have, this is 3 to 4, so it means here between here is going to be 2.5, 2.6, 2.7. So this is the value, 2.7 is the value before the 0 scale of the main scale. So 0, the reading before the 0 reading of the vernier scale is going to be the main scale. So you are going to have 2.7 centimeters. 2.7 centimeters. So that is the vernier scale. Then that's the main scale. Then in the vernier scale, we are going to count at which time are they called, is there coincidence. Coincidence is in, from the diagram it is not that clear, but you can see that the coincidence, where there is a coincidence, where there is a coincidence of the vernier scale and the main scale is 4. So we are going to multiply 4 times the accuracy, which we said is 0.01 centimeters. So if you do that, you are going to have 0.04 centimeters. If you add this, you are going to get 2.74 centimeters. That is the reading of that. Example 2. So the value before 0 of the vernier scale is going to be 7.6. So you have 7.6 centimeters. Then where there is a coincidence is 4. So 4 times 0.01, you're going to have 0.04. If you add that, you're going to get this. Micrometer screw gauge. Remember, you can be given a reading like this, then you're told to draw the vernier. If you're given a reading like this, you're told to show it on the vernier. You're supposed to get the main scale. You're supposed to get the vernier scale. Then you're supposed to get the how many, at what point are they colliding. Then you'll be able to go. Micrometer screw gauge. What is micrometer screw gauge? It is a device used to measure small lengths. It has an accuracy of 0.01 millimeters. It has 2 scales, the sleeve scale, the thimble scale. The sleeve scale is divided into upper and lower scales, with the upper division in millimeters and lower division in 0.5 millimeters. Thimble scale is divided into 50 equal divisions, e.g. division consisting of 0.5 0.01 millimeters. So this is what is called micrometer screw gauge. This is micrometer screw gauge. This is zero adjusting screw. Then you have ball, you have maple, jaws, sleeve scale. Then you have thimble. Then you have richet. Then that. The reading is taken in two steps. The reading on the sleeve scale is read at the point where it touches the edges of the thimble in millimeters and a half millimeters. The thimble scale is read at the point where the center line of the sleeve is parallel to the thimble scale of the division. This is what we are talking about. Give the reading of this. So the solution of that, what is the solution? Take a look at the diagram. You have a coincidence at 45. Value after that. So this sleeve scale reading is 3.5 millimeters. So how is 3.5 millimeters coming, Mr. Victor? So you have 0, then you have 1, 2, 3, then you have this one here, 3.5 millimeters. Then it is colliding at 45, then you multiply by the accuracy, which is 0.001. So if you do that, you are going to get 0.45. Then you add this plus this, you are going to get this. Let's come to example 2, sleeve scale reading. So it is at the fourth mark this. Then it is colliding at which point? So it is colliding at 32. So we multiply 32 times the accuracy of 0.01, you get 0.32 millimeters. Then you add, you're going to get 4.32 millimeters. Calculating the size of a molecule. That is now oil drop experiment. Under oil drop experiment, we'll be seeing calculation assumptions made, uses of lycopodium powder. Why do we use that? The assumption. We are going to see all that as we'll be revising questions, so that we see more about how it is set. So this is also another interesting part which is always being set. Calculating the size of a molecule. Both the volume and the area of the drop can be calculated using the formulas. So here 4 over 3 pi r cubed, and the area is pi r squared h. So what are some of the assumptions made in the oil drop experiment? So the first one, the area of the patch is assumed. The volume of the patch. So the first one, you say the volume of the drop is equals to the volume of the patch. The volume of the drop is equals to the volume of the patch. Then the drop is assumed to be spherical. The drop is assumed to be spherical. The drop is assumed to be spherical. So those are just some of the assumptions which are made. We'll be seeing more as we do calculations and as we interact with questions of KCSE. There's some like it is 1 molecular peak. So for example, a drop of olive oil whose volume is 0.12 cubic millimeters was placed on a surface of a clean water. The oil spreads and formed a patch of area 6.0 times 10 raised per 4 millimeter square. Estimate the size of the olive this. So you say the volume of the patch is equal to the volume of the, so the volume of the drop is equal to the volume of the patch. The volume of the drop is equal to the volume of the patch. Please kindly think of something like that. So we are given the area. The area given with that. So we have said the volume of the patch is equal to the volume of the. So volume is 0. That the area of the patch is this. So the volume is equal to area times thickness of the patch. Therefore, thickness of the oil patch is volume divided by area. So if you do that calculation right, you are going to get this. Suppose an oil drop has a volume of 0.1 and forms a film with a radius of 10 centimeters. Calculate the thickness of the film. So the area of the film is pi r squared. So thickness of the film is equal to volume divided by area, hence 0.1 divided by that 1400. You are going to get this. Number 3, chapter 3 of this, it is going to be turning effect of force. Turning effect of force. Turning effect of force. Turning effect of a body is called the moment of that force. Turning effect produced depends on both the size and the force and the distance of the pivot. The turning effect produced depends on both the size of the force and the distance of the pivot. The moment of a force about a point is the product of the force applied and the perpendicular distance from the pivot to the line of action of the force. Hence, moment of a force is equals to force times perpendicular distance. The law of moment states that when a body is in balance or is in equilibrium, the sum of the clockwise moments equals to the sum of the anti-clockwise moments, and the SI unit is Newton meter. Remember this, very important. You'll be told to state the law of moments. It states that when a body is in balance or in equilibrium, the sum of the clockwise moments equals to the sum of anti-clockwise moments. That is it. And I've said the SI unit of moments is Newton meter. Example 1. A uniform rod of negligible mass when a weight of 3 Newton is at A. Weight of 3 Newton is at B. A weight of W is at C. What is the value of weight W? So this is what we are going to say. We have said moment is the product of force and perpendicular distance from the turning point. So you have this from point A to 0 we have 3 meters. Then from point B to turning point pivot we have 1 meter. And you have said the law says the sum of the anti-clockwise moments is equals to the sum of clockwise moments. So we are going to have 3 Newton times 1 plus 3 Newton times 3 is equals to W times 3 Newton. So that is what is happening here. So anti-clockwise moments, 3 times 1 plus 3 times 3, you are going to have 12. Then anti-clockwise moment, you are going to have 3 times W, 3 times W, you are going to have 3W. So 3W is equals to 12. So W divided by both sides by 3, you are going to have 4. That is it. Let's come here. This is now of angle. This one now of angle. The following bar is of negligible weight. Determine the value of x if the bar is balanced. So you can see this angle here. So the diagram is not that clear, but the solution is this. The distance from the turning point to the line of action can be determined as, so the clockwise movement, so you have 10 Newton, then you don't have x here, so x is the distance in Newton, then you have 60 centimeters, then you have an angle here of 150, then you have a force of 10 Newton. So the clockwise moment is going to be 10 times 30, you are going to have 300 Newton. Anti-clockwise moment is equal to 10 times x here. 10 times x, you're going to have 10x. Using the principle of moments, we say that the sum of the anti-clockwise moments is equal to sum of the clockwise moments. So you're going to have 300 Newton meter is equals to 10x. So for us to get x, divide both sides by 10, you're going to get 30. Again, this, you have 10 Newton, 40 centimeters, you have 10, 20 centimeters, you have 10 Newton. Then you're told to find x. Very simple. So the sum of the anti-clockwise moment is equal to clockwise moment. So clockwise moment we are going to have, so you have 15 times x plus 5 times perpendicular distance is going to be 20 plus x. So you're going to have x plus 20, x plus 20, not x times 20, it is x plus 20. That then anti-clockwise moment, you're going to have 10 times 60, 20 plus 20, 20 plus 40 is 60. Anti-clockwise moment, then so this plus this is 60 times 10, that is what's happening here. Then you have 10 times 20, that is what is happening here. You're going to have 800 Newton centimeters. So the sum of the anti-clockwise moment is equals to clockwise moment. So here you're going to have 800 Newton centimeters is equals to 15x plus 5x plus 100. So you're going to have 20x plus 100. That then you collect terms. So 100 closest equal sign. You're going to have 800 minus 100. You're going to have 700. So you have 20x is equals to 700. X is equals to 35 centimeters. Therefore, the length of the bar. So with length of the bar, you're going to add 40 plus 20 plus x plus 20. Remember, x is 35. So 40 plus 20 plus 35 plus 20 is 115 centimeters. Right. The lever. A lever is any device which can turn about a pivot or a fulcrum. The applied force is called the effort and is used to overcome the resisting force called the load. We use the law of moments in the operation of levers. Consider, you have an example, you have this. So how do you calculate the effort? Here? You are given a distance of 200 centimeters, 30 centimeters. What are we going to do? So we say the sum of the anti-clockwise moment is equals to sum of the clockwise moment. So you're going to have 20 newtons times 30 is equals to 200 centimeters times effort here. So it means clockwise moment is going to be effort times 200. Clockwise moment is going to be 200 newton times 30. So if you do that right, you're going to have 200 effort is equals to 6,000. So divide by both sides by 200 so that we get the effort. You're going to get 30 newton. Chapter 4, equilibrium and center of gravity. Equilibrium and center of gravity. Equilibrium and center of gravity. We say, what is center of gravity? Center of gravity, or COG, is the point of balance of a body in which the total weight of the body seems to act through. Center of gravity is the point of balance of a body in which the total weight of the body seems to act through. That is all about COG. So let's calculate. It is still applying the same law we talked about. The sum of the anti-clockwise moment is equal to clockwise moment. Then COG is just the midpoint. Center of gravity is the point of balance of a body in which the total weight of the body seems to act through. For example, we have a calculation there. The figure below shows a uniform bar of weight W and the length is 80 centimeters. If a force of 20 Newton keeps it in balance, determine the weight W of the bar. You remember, you are told it is 80 centimeters. So it means the COG is at 40 centimeters. 40 centimeters. Then the distance from 20 Newton to the pivot, I can see it is 10. So what these people want, they just want you to calculate the same rule. The sum of the anti-clockwise moment is equal to clockwise moment at a given point. So taking moments about the pivot, clockwise moment is going to be W times 20. W times 20. Then anti-clockwise moment is 20 times 30. 20 times 30. So 20 times 30. So clockwise moment is equals to anti-clockwise moment. So 20W is equals to 20W is equals to 600, then W is equals to 30 Newton. We will be seeing all these in a real question where we'll be revising KCSE question, mock, pre-mock and post-mock questions. I'm doing this to help you cover syllabus faster so that we have ample time to calculate everything as we go. As I said, this channel is here to stay. It is here to help. Kindly subscribe. Once you are done even with your KCSE, recommend it to some other students who are still learning. Learning is a continuous process where we get knowledge every day. Parallel forces and equilibrium. For a body to be in equilibrium, neither moving nor rotating, under the action of parallel forces, the following conditions must be satisfied. For body to be in equilibrium, there are some conditions that must be satisfied. 1. The sum of upward forces must be equal to the sum of downward forces. That is correct. You must remember that. We are going to use them in calculation. 2. The sum of clockwise moments equals to the sum of anti-clockwise moments. That is a law that we said in our turning effect of force topic. The two are called the first and the second conditions of equilibrium respectively. Example: a uniform rod of length 1 meter is hung from a spring balance as shown and balanced horizontally by a force of 1.6 Newton. Determine the weight of the rod reading on the spring balance. So the first thing I want to say, let the weight of the rod be W. Weight acts at 50 centimeters mark because we are told it is a meter rule. Remember 1 meter, that is 100 centimeters. So weight acts at the center COG, which is 50 centimeters. Therefore, taking the moments about the point of suspension, clockwise moment is equals to W times 0.2 because already 30 centimeters is taken. So our COG is going to be somewhere here. So it is going to be 20. So that's why we are using W times 20. Then anti-clockwise movement, we are going to have 1.6 times 30 centimeters. If you change it to meters, you are going to have this. Using the law, we say the sum of the anti-clockwise moment is equals to clockwise moment. So we are going to have 0.4 is equals to 0.2 W. Then we are going to have weight is equals to 2.4 Newton. If you are asked mass, what is the mass of the meter rule? Kindly remember, we said how we calculate mass. We say that W is equals to mg. M is equals to W divided by gravitational pull. So mass is equals to weight all over gravitational pull. Upward forces is equals to downward forces. As upward forces is equals to downward forces, so a force acting downwards is equals to a force acting upwards. So what are the downward forces? So downward force is 1.6 Newton plus the weight of that particular meter rule, which is 1.6. So we are going to have 4 Newton. Upward force is equals to downward force. So reading on the spring is going to be 4.0 Newton. Correct. Question 2. A uniform rod is 1 meter long, weighs 5 Newton. It is supported horizontally at one end by a spring and the other end rests on the table as shown below. A mass of 2 kg is hung from the rod as shown below. Determine. So this is what you're talking about. This is what you're talking about. This is what you're talking about. Number 1, we are told reading on the spring balance, reaction force from the table. The first thing, 2 kg mass and the weight of the rod gives anti-clockwise moment, while the spring balance provide anti-clockwise moment. So 2 kg mass and the weight of the rod gives us clockwise moment, while the spring balance provides anti-clockwise moment. Clockwise moment is equals to 2 times 10. 2 times 10 we change into force. So we're changing 2 kg to force. 2 times 10 times 0.4, that is now the perpendicular distance, 0.4 plus 5 times 0.5, that's going to give us 10.5 Newton meter. Anti-clockwise moment, we are going to have S times 1, S times 1. So this now up to here, it is the turning force. So for this one here, for S, perpendicular distance is going to be 0.4 plus 0.6, you are going to get 1. That's why you're calculating here. Then you're going to have 1S is equals to 10.5. So it means that S is equals to 10.5 Newton. You say the sum of upward force is equal to the sum of downward force. So you add downward force, which is going to give you the sum, which is equal to the upward force. Stability. What is stability? This is a term which explains how easy or difficult it is for an object to topple over and when a force is applied to it. Factors affecting stability. Base area. The bigger the base area, the more the stability. Position of the center of gravity. The higher the center of gravity, the less stable the body will be. States of equilibrium. You have stable states. If a body is displaced by a small amount of force, it returns to its original position. Unstable equilibrium. If a body is displaced by a small amount of force, it toppled over and does not return to its original state or position. Neutral state. A body is at rest in whichever position it is placed in, i.e., it does not rise or fall when displaced. So as you can see in the diagram, you have at the stable state, you have unstable state, then you have neutral state. Application of stability. Applications of stability. It is used mainly in the design of motor vehicles, i.e., racing cars. They have a low and wide wheelbase to increase their base area. Double-decker buses, they are manufactured with a low center of gravity by putting their chassis and engines as low as possible. Kindly note that we have covered up to topic 4, chapter 4. Now we will proceed from chapter 5. Have a nice time. This is Teacher Victor. Kindly subscribe to my syllabus coverage, tutorials, and KCC. You can have a look at KCC revisions, post-mock exams, pre-mock exams, so that you get familiarized with what are being said in the topics as we discuss as we move forward. Kindly have a nice time. I'm Teacher Victor.